and we'll be pretty short. All right, so today's topic is science in the early childhood classroom. And there are really two aspects of science learning in the preschool years, and that is the process, the doing, the how, and the content, the stuff, the knowledge, the what. So the scientific process is children learning about asking questions, learning about inquiry, learning about how to gather information about the questions that they have, how to have a process there to think about ways of answering the things that they're curious about. Now, young children, we know, have some limitations to their thought. We know that sometimes they have sort of magical thinking. We know that sometimes they have difficulty with what we would consider as a logical progress of thought. We know that they can be egocentric, and all of those limitations on their thinking means that some of the times the ways they answer the questions will be in ways that we know aren't accurate. And so this scientific process area is really uh, fostering in them some critical thinking skills, which are really so important for us as we navigate this world today. The other piece, which is science content, is knowing the it's not social arbitrary knowledge, because these are factual things about the world, but it's discoverable knowledge. So it's not just for an adult to transfer to us, to just say, here, let me write this down and you read it. It's for children to investigate and develop and construct that accurate knowledge of the scientific content. So concepts, facts, information. Sometimes we used to use the word TFPs, which was terms, facts, and principles. What do we know? What is this shared knowledge that we have uh, that we can use as a basis for our further investigation? Now, in Tennessee, in our 10 ELDs, there's the 0 through 4 and the age 4 and 5. There's those two different sets of standards broken down by age. And the science standards are organized a little bit differently in the two age groups. When you look at those in your readings, uh, in your reading, I just kind of distill them down into these four groups, and just kind of loosely organized them that way. The first group was scientific inquiry and science basics. So this is really that fostering the process part. The other two categories are more content. And so that's physical science, life sciences, and earth sciences. And I wanted us to remember that when young children are curious, their curiosity is driven by their attempts to make sense of the world around them, to make sense of the things that they're observing. And so as their cognitive development is unfolding and uh, progressing, both biologically, in terms of the physiological development of their brain, those blooming and pruning and making those connections, and fine-tuning those connections. It's also an increase in sort of their metacognition, their ability to think about their own thinking. And so their growing awareness of observations, the observations of things they're seeing, how they think, and how that is reflected by what they do. So children's attempts to make sense of the world gives us some insight into their growing understanding about the world. And one of my favorite kind of examples of this is it was from a mistake I made. I I had a child who was 4 on a playground ask me, "Why does the wind blow?" And if you think back to our child guidance kinds of things, I should have Well, actually, let me tell you this in terms of science. The best answer I could have made was to reflect back. You are curious about the wind. Let's find out how it blows because that's how you can support children's learning. How can we find out more about that? How could we get some nonfiction books about science and maybe we'll read about that. Maybe we can do some experiments. How can we progress? But what I did, the mistake I made that day, is I turned their question around and made it a question. I Instead of saying you're curious about the wind blowing, let's find out some more. I said, well, why do you think the wind blows? And I'm kind of glad I did because it gives me this great example that I use when I talk about Piaget. And you may have heard this example if I told you in child development about children making schemas. But this child looked at me and thought about it for a moment and said, I think the wind blows because the trees fan the air. And if you think about that, it makes perfect sense to this 4 year old because every time he had ever felt the wind blow, the trees moved. And also, he'd felt a fan move, and I can feel it right now. I can feel the air moving from that. It makes perfect sense that the trees are moving and blowing the air. It's a correlation causation thing, right? It's pretty classic for adults. Every time I feel the wind, as the trees are moving, they must be causing that. We all know that's wrong. We all know that trees don't move, but in the magical animism kind of thinking of a 4 year old, that made perfect sense. And in that moment that child had figured this out, no amount of me saying, well, no, actually, the hot air is less dense, and so it expands and rises up above the more dense cold air. And during the daytime, the sun comes down and it heats up the land more slowly than the water heats up. So the air over the water becomes less dense and rises, and it causes this circle. But at night, the air over the water cools off faster and it causes it to go back this way. And there's these low pressure zones and high pressure zones, and they cause fronts where they come together and blah 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 wah, wah. That makes no sense, right? It's there's something accurate about it, but it doesn't make any sense to that 4 year old who knows the wind blows because the trees are fanning it. They've got this figured out. So my job is now I have this insight into their uh, wrong hypothesis here, or wrong theory. It's not a hypothesis, it's a theory about how the wind blows. And so my goal now is to ask challenging questions. So if you think about Piaget and assimilation and accommodation, that's a good metaphor here. Every new observation this child makes, they're either going to assimilate it in to that existing theory or accommodate their existing theory around that new observation until they get to the point called disequilibrium where they can't stretch it anymore and it's just not going to fit. So I ask questions about, oh, how does the wind blow in the desert where there's no trees? Or, some kind of open-ended kind of questions there that challenge and move that erroneous theory towards disequilibrium where the child has to reject it. And so that's one of the ways that science takes a form in preschool years, is asking those kinds of open-ended questions and giving children the opportunity to explore and manipulate things and conduct their own experiments that can challenge those wrong kind of theories, those erroneous kinds of ideas. Years later, my daughter, when she was about 4, asked me that same question, and I said, well, I could experiment on her. And I said, I don't know what makes the wind blow. And she thought about it, and she explained that it was because of cars driving. They push the air and make it blow, which makes sense because every time you roll down the window in the car, you can feel the air blowing. Uh, so those are just some examples of the kind of erroneous, wrong theories that young children come up with that is based on their kind of magical thinking animism. It's based on those ideas that it's not egocentrism exactly, but it's a failure of logic, right? So that's why it's important that we provide children with experiences in which they can investigate questions, which they have materials and opportunities to conduct their own little experiments, that they can use inquiry, that asking of questions as a way of learning. And so scientific inquiry is based, this is very similar to just thinking of what the scientific method is. Observing those firsthand real experiences, identifying what the question is, making a prediction about what will happen, testing those ideas, and then analyzing it and making conclusions. Now, the first thing I'd say about this list is that's very much like what the scientific process is, and that's what our sort of goal is in teaching science, is to teach children that sort of scientific method. The second thing, let's walk through that example of the child with the trees moving and blowing the wind. So observing firsthand experience, they saw the trees move every time the wind blows. That helped them identify that question. Why does the wind blow? Well, it's because the trees are moving. So their prediction is every time that they see the trees move, they'll feel the wind blow. And see, they're thinking kind of backwards there. Um, Giving them opportunities to test it and then analyze and make conclusions. And so that child's conclusions was that the trees caused the wind to blow. And then a part of the scientific inquiry method is to share findings with others. So this could be telling them, it could be making a display, it could be writing it down. On up to in graduate school, it's writing a dissertation or a journal article or a book. So that scientific basic process, what I'm trying to say is it works the same across development. So children are using inquiry when they're asking questions about the world, when they're asking, why is this? What does this do? How does it do that? When they are exploring things, when they are working with things, when they're manipulating things, when they're watching and making observations, when they're using tools like magnifying glasses or uh, microscopes, when they are describing those things that they've seen, all of those are parts of the inquiry process that we see young children engaged in. So I've kind of talked about this already. There can be this immaturity in thinking and these misconceptions that reflect children's understanding. Now, here's the thing. I said before that no amount of me saying, oh, low pressure, high pressure, blah, 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 that's not going to make any sense to this child who's already got it figured out. It makes perfect sense to them the way they figured it out. And so you can't just come up and say, no, that's wrong. Here's the real reason for it. You've got to understand that the misconceptions that they're telling you reflect their current knowledge, their current beliefs, their current maps in their mind of how things are working, their theories. And so the teacher's job begins to be to facilitate them and moving them towards rejecting that. And so asking open-ended questions, asking them, well, what would happen if? How could you do that a different way? Giving them materials to challenge that thinking, and demonstrating an attitude yourself that's not, oh no, that's not right, but rather it's, let's think about that. What would that mean? What would happen? Huh? What would we do with this? And letting the child fill in those blanks, right? Instead of answering it for them, encouraging them to think and them to do those either mental or real life experiments to see how it plays out. It's important that we uh, not see science as isolated. it's this here's the science table, there's the stuff over there, there's science time. That's not it. So science is going on whenever we're out on the playground and we're thinking about nature, for example, we're doing life science. It's also important that science is supported by our choices in terms of literature, so that there are uh, nonfiction books available in the class library, developmentally appropriate ones that are readings and discussions have science related content. Now, it doesn't mean that I'm not saying that all of our readings and discussions are science related. There's a time for uh, cultural things like fairy tales and folk tales and Three Little Pigs that aren't necessarily science. I guess we could have some science about the wind blowing down the twigs versus the bricks. But my point is not everything has to be science related, but there should be some nonfiction mixed in with the fiction. There should be some developmentally appropriate access to science related content in children's books. Make sure those books are accurate and that they're DAP, and recognize that children, and we've talked about this many times, they're actively constructing knowledge through play. So allow them and encourage them to explore, to test their concepts and theories, to develop skills in logic and problem solving. Um, my PowerPoint's doing some weird little pop-up things, orders there, so excuse me for that. Um, it's important as teachers that we don't sometimes if I'm going to say something here, and I don't want anybody to misunderstand this, but it's not important that an early childhood teacher be an expert in physics and chemistry, but it is important that they understand enough of the basics of physical science, life science, earth sciences, that they're not passing on misinformation, that they're not passing on things that aren't accurate. Okay. So make sure that you're understanding, if you want to have a topic about dinosaurs, make sure that you are accurate and up to date on your thinking about dinosaurs. I'm not even sure whether Brontosaurus is a dinosaur or not. It was, and then it wasn't, and no, it was again. Is it today? I don't know. So I want to go look that up. I want to make sure I know. I can look it up on a reputable kind of place on the internet. I can look it up at the library. I can ask people in my community. Um, I can look in children's nonfiction books, but I want to make sure that those are up to date and relevant. One of the best sources about content knowledge for young children is nonfiction children's books, but you need to recognize that they can be outdated. The knowledge that we have moves. Just because we knew that this was true at one time, we may it may not have been a brontosaur. It may have been something else. So we need to make sure that our knowledge is current and the best knowledge that we have. Another example of thinking about your community is if I had children on my playground and they ask me what kind of plant that is, well, I want to be able to tell them what it really is. And if I don't know my plants, I could ask somebody, uh, whether it's someone I know or someone um, in the local community that knows. So encourage exploration, give time for hands-on manipulation, facilitate discovery by listening to what children are saying, and when those naturally occurring times come, capitalize on those. So when children find that interesting bug, or when children have cut up that flower, well, let's see what those parts are inside that flower. Uh, So look for those naturally occurring moments and use concrete, real things for investigation. This isn't a time, early childhood is not a time for worksheets or circle this or which one of those match. It's a time for real hands-on digging in the dirt and splashing in the water. There should be science in all those different parts of the day. So your book or your reading has a lot of different list of different materials to support discovery. These are just some examples of tools, materials, and it doesn't have to be limited to a specific science area. It's good to have a science table that has things like magnifying glasses and uh, I'm thinking of the really broad kind of microscopes. Uh, but these kind of things can be throughout the indoors and the outdoors. Things like measuring tapes, things like scales, so that children can investigate their discoveries. When we think about families, ah, well, thinking about families, I lost that, but it's important that we share our knowledge about the importance of science with families and get them involved in supporting children's learning about science.